So, yesterday we were looking at the energy absorption by basically the plastic deformation and the hinge formation. All that depends on the plastic capacity. Plastic capacity depends on the strain and the rotation. Basically if you look at the formula what we have got for a simply supported beam with a central point load 4 MP by L. So, that MP depends on the capacity of the member. So, basically what we are trying to look at, one of the requirement was Marshall criteria, which is empirical, trying to limit what could be the maximum rotation possible. The second one, we just need to look at the geometrically admissible rotation, because if the rotation is too much or the delta is too much, the beam will already would have broken into two pieces. For example, you look at this picture, you apply a load like this and you keep increasing the load. When the delta becomes too large, then that cannot exist, because the length extension or the strain in the beam, this half of the length, if it is considerably smaller compared to the displacement, the rotation is larger, the beam has to break. So, that is what we are trying to derive a relationship between the strain and the rotation. So, basically you just see here using small angle principle r theta, you can find out a relationship between delta and L by 2 theta. And similarly, you use a Pythagoras theorem to find out the length extension is delta L because of the strain in the member, and it just express in terms of L by 2 delta L square plus, and expand this and basically try to ignore the second order terms delta L square and delta L, and finally you get a relationship between the delta L and thetas. Basically you get some relationship, and then the strain can be defined as you know very well, change in length over the half length of the member, and substituting that you will get a relationship, the maximum rotation that can happen if you know what is the strain, because the strain is directly proportional to the extension of the half member, and that is basically defined as a strain. So, we can basically look at what will be the allowable strain. For example, if it is in elastic range 0.2%, then you can find out what is the rotation maximum allowable, and if you go into elastoplastic, you could allow either 2% or 10% or 15%. So, depending on what is the strain that you are trying to allow, you can relate the indirectly the strain is related to your delta. Only what we have done is little bit of approximation. All this is required only just to get an, when you do a nonlinear second order analysis in a computer, you do not need to really worry about all this, because automatically takes into account. Here we are trying to derive a kind of relationship between the strain and the rotation, because many times you will do a hand calculations, simplified hand calculations. So, one is a Marshall's criteria, which is highly empirical based on experiments, what could be the maximum strain that you would like to allow, which will produce a corresponding rotation, and in here we have just derived a geometrically admissible relationship between the rotation and the strain, and we should actually look at both, and whichever gives you the reduced value, we should use that for our calculations. Now, a simple example, basically I have given you how do you design a boat impact protector. You see this picture, I think by this time you know what is the configuration. Basically a well platform with 4 legs, and wells are located on the inside. As you know very well, we want to locate the wells inside to protect against any of this kind of impact. Basically, is highly dangerous. If you have wells outside, you know what will happen in case of impact, the first thing will get damaged is the well. So, most of the time wells are kept inside 4 legs with the well protected. Also the risers, you can see in this green color, risers means the transportation of fluid from platform to platform or platform to onshore. All of them are kept inside just you know for the reason of safety. But sometimes what happens, you plan a platform and then in future you get more oil, you won't say I do not have riser, I will not take the oil. So, you need to add additional risers, is not it? At that time you add the risers only outside, because you cannot go inside and add. So, when such things are planned, you have a riser coming in future, or maybe unforeseen risers, several times that will happen. You plan a platform for 20 years, but still oil is still producing, you will not stop, you will recertify the platform for another 5 years, add another riser, add another equipment. Sometimes happens, because the quantity of oil available could be estimated at the initial stage, to some accuracy, but not 100% correct. It could be lower or it could be higher. So, that scenario you have additional risers coming outside the legs, because you cannot install inside. Now, we need to protect this. You see in the red color what I have drawn, just a simple frame which will make sure that it is protecting the risers against any impact. Now, you see here there are two connections we have made, one to the one left side leg, another to the right side leg. Why we did not make a connection here? Because that member also may not have sufficient capacity to absorb, and also if that one deflects, what happens? It will go and damage the existing risers inside. So, you have to pick up the correct points in such a way that you do not damage the structure. So, basically that is the idea behind. You do not want any of these existing facilities to be affected because of the new additions. So, when you see this type of design, what we are trying to do is come up with a design in such a way that after impact you do not get damage either to the structure or to the facilities that we are looking at. So, this H will need to be designed in such a way that after impact the deflection does not make the structure to be in contact with that type of facilities that you are adding with a margin, probably half a meter or few hundred millimeters. So, design a boat impact protector for a vessel size of 8,000 tons, velocity of approach is 1.5 meter per second, and yield strength is given, and stern impact, length of the legs or the length of the member between legs is 15 meter, and dent depth not to exceed 25% of the diameter, and use approximate methods, not computer analysis, just to arrive at a preliminary dimensions. Later on you can do all your computer analysis design, but just to get an idea. So, how do we approach the problem? First of all, we need to fix up a diameter, because diameter also not given, no, you see there the diameter is not given, only the spacing is given. So, we need to come up with an idea what could be the potential diameter. So, you need to go back to your basics span to depth ratio, basically I think you might have studied in your concrete design, steel design, simple ideas, span versus depth could be in the order of 10, 15, 20, isn't it? So, do not keep it 100, it will automatically become a rope, isn't it? So, basically span to depth ratio is something that all civil engineers should keep in mind, so that when you start a geometry configuration, you are starting in the right direction. So, typically for a supported at both ends, span to depth ratio between 15 to 20 is a good number, isn't it? So, you start with that. So, based on that I have just assumed a diameter of all the given parameters. I just take a diameter of 1 meter. Looking at it, I would be able to get the 15 meter, means I should start with 1 meter. Maybe later if I am not enough, I can go for slightly bigger. So, start with 1 meter I have this, and thickness I have just assumed as 25, as I mentioned yesterday, d by t ratio of about 40, simply start from there. All other parameters are given, and basically the energy of impact is calculated as 9,900 kilonewton meter, basically half mv square, everything is given, simply calculate, and modulus of elasticity you will require for that empirical formula, just for the sake of calculations. So, diameter to wall thickness, moment of inertia, and the plastic capacity of the part of the plate, basically the pipe, the plate made of that pipe, basically that local moment of inertia, and then the plastic capacity of the tubular section itself, as a whole section. So, that is small mp, I just to differentiate, and then the dent depth is taken as 25% of the diameter, and then force due to dent depth, this formula which I think we were looking at from the API recommendations, substitute all the parameters, you get 3,616 kilonewton. So, basically for a 25% diameter of the dent, you get a dent force of something around 3,600. Now, basically the plastic capacity and plastic moment capacity of the pipe and the plate has to be differentiated, both will be used in different places, and then you find out what is the energy absorbed due to dent, which is the empirical formula that you have already, about 600 kilonewton meter, and the elastic deflection of the beam you know very well both ends are assumed to be fixed. If it is not given, if you go back to the configuration, you will be able to get fixity, but not 100%. If it is not given, use 100%. For examination purpose, we may actually give 60% or 70%, but in this case directly. And then energy absorbed due to the elastic deflection of the beam, basically the force times displacement, and then the plastic collapse load, which we derived for a simple point load is, this is a fixed conditions, sorry, basically 8 MP by L, and you get that much of plastic capacity load. And then the maximum strain limit you need to calculate. For elastic, we know very well it is 0.2%, but for plastic strain is taken as 20, which is what is recommended by Marshall. So, you get around 4%, and basically the rotation maximum possible, which we derived a formula just now, geometrically admissible, is 16 degrees, and displacement at the plastic hinge location is 2.2 meter. So, you can see here is just going so much, and then energy absorbed due to plastic displacement, which is basically the plastic collapse load multiplied by the displacement, which is 9,000. So, you can see the larger energy is being absorbed. Basically, the energy absorption due to dent is very small, about 600, I think, about 600, and then the elastic is basically about 126, very small. But if you look at the plastic deformation at the time, that means this protector is going to be sacrificial, it is going to fail. That means one time impact, the next time you have to go and replace. So, this is what the condition will be given to you, whether it is a replaceable protector or permanently the protector should not get damaged. Depending on the situation what you are given, you should be able to design it. So, in this particular case, it was not mentioned whether both impact protector member basically have not given whether it should be sacrificial or permanently to be designed in such a way that it should not get damaged. So, in this particular case, what I have done is I have designed in such a way that it is a replaceable protector. The reason why I decided to do so is basically an external member. For example, if this is a part of a jacket member and which requires for jacket integrity, I may not assume that way, because once the member get damaged, the jacket becomes unsafe. Whereas, in here it is only a peripheral member, it does not contribute to the global integrity of the jacket system. So, I can design, if it did get damaged, does not matter, I will go and replace next time after few days of the damage. So, that is why. So, you see here the total energy absorption is 10,000 kilonewton meter. So, I have definitely satisfied the energy absorption criteria. Basically, the energy required and energy absorbed is higher. So, basic idea is the two things to note down. We have got all three components. One is the elastic, the dent formation, then the elastic deformation and the plastic deformation. What is not taken into account is the global jacket displacement, which will not be able to calculate by manual calculations. What you need is a computer analysis. You take this force which you have calculated from plastic collapse, which is transferred to the jacket legs. You will do an analysis of the jacket and then find out what is the displacement, and that will be added to the total energy. In this particular case, we are, that is why I have put use approximate method by which I can ignore the global platform deformation. So, this is a typical example by which you can utilize the design methods for dent, elastic and plastic deformation of the simple beams, whether it is fixed or pin or other boundary conditions. You could, the reason why we derived all those formulas is for that. One is we derived all the collapse loads, and then basically the strain and the rotation relationship, and basically the relationship between the energy and basic parameter from dent and dent force to the displacement. So, all those relationships are used just to arrive at the energy absorption versus the force introduced. The next one what we want to see is, you look at this picture, we will go back to this picture. In case if this joint fails before this hinge formation, So, what happens is the energy absorption criteria what we have set, E dent plus E elastic plus E plastic, may not be able to achieve in case if this joint fails, because we have assumed that the joint is fixed joint and it is going to take that much of reaction, whatever the reaction, the impact force is P collapse we have calculated, half of that is going to go to this joint and that joint needs to take like what you have done for a punching shear capacity. Now, we need to evaluate the punching shear capacity and make sure the capacity is higher or at least will not fail when the collapse load occurs here. So, that is the idea, otherwise that collapse load or collapse energy what we have calculated may not be able to achieve because of the joint failure. So, we need to look at the ultimate joint capacity and find out whether we are able to achieve this. If, as I mentioned earlier on when we were deriving the formulas for joint capacity design, all of them are ultimate. You will remember when you are looking at P allowable will be having Fy T square Qf Qu divided by factor of safety which is 1.6. So, if you remove the 1.6, that is actually the ultimate capacity of the tubular joint. So, then we can find out at what load that ultimate capacity is achieved. So, if you look at the three formulas which I have just written down here, only just a symbol difference, basically in API they put instead of T they have P by P ultimate, just a notation. Otherwise, this is the formula that previous revision of API you could see here, which we were trying to derive relationship between the moment and the axial load. Earlier, I think yesterday we were trying to do. Earlier revision of API was using this, and the recent API they have just changed to this, and the reason is this is for tubular. In fact, this is the correct methodology. In fact, you will get this term when you derive for circular section, whereas you will get this for rectangular section. The stress pattern around the brace tubular interface is so complex, it is not going to be a circular because you will get a elliptical interface, you may get a stress variation is not uniform. So, API have done a joint study with the industry people in UK, and they have come up with the recommendation that we should use this, which is going to be conservative in the high moment areas. So, basically this is the one that we are going to evaluate for joints, except that in this case we will remove the factor of safety because we are looking at the ultimate capacity. Whereas, the UK they still use the combination of this plus this. You see here you have got the linear term coming from the first one and the non-linear term coming from the second one. So, there is quite a bit of difference between different codes, but of course, if you look at the ISO codes and the API recent one, they use this interaction between the axial load and the. So, you will have to evaluate the capacity of the joint, make sure that the load at which the collapse occurs will be substituted here, and correspondingly the joint should not fail. When you just overplot the previous revision of API and the new version of API, you see a difference between some areas. You see the red color is the old API, and the dotted blue color is basically the new or revised. Some areas the new equations are actually under predicting and basically not so good, but still you go back to, if you look at this one, this is even worse. So, that is why the UK guidance notes has been withdrawn, now no more valid, because all the UK codes and standards they are going back to ISO codes. In fact, most of the British codes are now is getting one by one withdrawn because it is getting replaced by the ISO codes. So, maybe you do not need to see this. The next one what we are just going to look at is what we did was the impact and local member, local joint, and then we just look at the global behavior. What happens is when the jacket is getting hit by a boat or a ship, we need to look at whether any reserve capacity available, and that is sometimes we call it reserve strength or reserve strength ratio. So, how do we get this? Basically, we set the design requirements. First, adequate individual brace capacity should be available, adequate joint capacity, which is what we were discussing just now, sufficient redundancy to alternate load path for failed braces. This is very important. I think the typical example will be the X brace. If you have single brace and basically if the brace is failed because of the impact, you do not have a alternate load path, and that is where many of the places you should insist that at least the first top 2 levels between you should provide a X brace. Overall system capacity basically nothing but the reserve strength ratio of the jacket before and after the damage, you know. So, basically you find out what is the strength original, what is the strength after damage, and if the reserve strength is in terms of ratio, if it is more than 1, you are safe. For example, you have a jacket, you apply a environmental loads of 1 year, 100 year, whichever the case that you would like to evaluate, and find out at what maximum load the jacket fails, that means collapses, and then do the same thing after one of the member is removed because the impact damaged the member, and then make the jacket to fail at what load it fails. Then you compare these two numbers. If these two numbers have substantial difference, exactly the ratio will give you the reserve strength available, and that normally should be greater than 1, and if it is 1, 1.1, 1.2, you are safe. So, that is what we are trying to evaluate, which is quite important in case of accidental loads. What will be the design criteria finally recommended by API is basically maximum strain of 10%, which is what we were looking at earlier on, 4% was there. Maximum displacement under impact is 1 meter, and mean value of Marshall's criteria for the rotation, basically calculate. So, you use that maximum strain of 10%, calculate the strain using the geometrically admissible relationship theta is equal to square root of 2 epsilon, and find out what will be the Marshall's criteria limitation. I think 2500 d by t square. So, you find out what that, whichever gives you the reduced rotation, use that, and with a limiting displacement of 1 meter. So, that will be the criteria acceptable by API as well as most of the industry companies, which I think just now we were trying to explain all these 4 parameters, basically kinematically admissible, shall not exceed Marshall's criteria. Typical impact locations. So, you see here this is basically an X brace, this is a non-redundant single bracing system. So, if one impact happens there, basically what will happen, the brace becomes unstable and fail, the system becomes portal. So, there will not be any redistribution possible, especially the horizontal loads. Vertical loads anyway will go through all the legs because it is carried by the leg system, whereas the horizontal system or horizontal loads will have sufficient overstressing of legs. So, that is why in this area, if you provide a X brace, is reasonably producing additional redundancy in the system, which will give you higher reserve strength ratio. When you apply the same load next time after this damage, if you apply the first thing, what will happen, the legs will fail. That means, before achieving a higher load, if the legs fail, the platform will definitely collapse. So, in here I have just given you a chart wherein the capacity of the member versus capacity of joint. When you design overall system, you need to make sure that there is no member or a joint isolated, basically should have capacities lesser than what is the minimum capacity is required. So, the overlapping zone is the safe domain of the capacity of the members, not one member, all the members, and capacity of joints put together. Some of the softwares, like for example, DNVC, some software has the capability to plot all the joints and members together to come up with a safe load that you can apply. But if you want to do it by manually, you will take a longer time, because each one you have to bring it into the chart, the allowable moment and the allowable axial load. Basically, when you look at the global structural behavior of a system, first yield, I think, which we were looking at earlier on last time when we were looking at a joint, basic load deformation curve, and first yield, first crack, and then ultimate failure. A similar idea, only thing is here is a multiple members, multiple joints. So, when you look at the first yield of a one particular joint or a member, does not mean that the system is going to collapse, because when you look at the overall system, bending moment may be maximum at one point, elsewhere bending moment is very less. So, that means one point may actually get into a first yielding stresses, but elsewhere in the whole system you may have stresses lesser than the yield point. And continuous increase of load, what will happen? You will see that any one of the point along the structure, several thousand members are there, you may form a hinge, and that is the point that we need to note down, because from there the system will start to behave unstable. You know, one of the member, this hinge formation is there, but remainder is still intact, but in another few 100-ton loads, what will happen is that member will become unstable. If that member becomes completely unstable, then the load from that member needs to redistribute to the neighboring members or neighboring joints, and that is the time basically will start relieving. If there is no redundant path, for example, if you do not have X brace, there is no redistribution, how it happen? One of the joints may get overstressed. So, that is the time you see here the load will, the capacity may actually drop down, but once that members gets overstressed, you may get slightly increased redistribution because of the local member in that vicinity. But ultimately the system will start failing when you have few more members get, you know, the plastic hinge formation. That means 1 member, 2 member, 3 member. At some stage the system will be just unable to take any more load because it is unstable, and that is the load that we are looking at, which we call it the total collapse load of the system or a jacket. So, that is, if you know that, and basically the ratio of the same load before and after damage can be evaluated. In the next picture, that is exactly what I have just depicted in red color and the black color, original structure versus the damaged structure, and that ratio will be your reserve strength ratio, depending on what is your load capacity, whether you are looking at 1 year or 100 year. So, in this particular case 100-year storm is taken as the reference load, and you apply the horizontal load, 100-year storm load, keep increasing with a factor of 1, 1.1, 1.2, 1.3 for both the structures, original and damaged. The difference will give you the strength available against damage. All the time we were looking at the horizontal axis as the deflection, you know, basically the deck displacement, what is the maximum amount that you can permit. The reserve strength ratio can be just defined as 3 cases, one is operating and the other one is storm, the third one is just an accidental case, which is what we were looking at just now, and this normally is used for recertification of platforms. There is no damage, but still we want to calculate the reserve strength ratio because the platform has been serving beyond the design life. For example, originally designed for 25 years, but I want to operate for 30 years. Now, that last 5 years, you know, basically several things have changed, environmental conditions have changed. When I want to recertify, I do not want to design the platform based on the allowable stress methods, because it surely is going to fail, because all the design conditions are different. Old design conditions is completely different from now, and members have corroded. So, I cannot design and verify the same platform which was designed 25 years back using the new design code methods. So, what we normally do is, for recertification of the platforms, we use the ultimate design principle, because it is only for a short duration of time, next 5 years, maybe next 2 years. So, that time we look at the collapse capacity and compare it with the design requirement, and that will be defined as a reserve strength ratio. All of you remember, recertification cannot be done using normal design principles which we are using, because for sure they will not be able to take the loads, because the design requirement 25 years back is very less stringent, number 1. The design codes are less stringent, and over the period of time design requirements have increased. For example, typically the live load requirements, the sea state conditions. Several years back we might have been using a smaller sea state, but because more and more information we have now, the design sea states are slightly higher, or well, you know, basically informed decisions are taken now, because we have lot of information. Earlier not much data was there, simply assume say maybe 16 meter, 17 meter, now it is in fact 19 meter, and we have got global warming, water depth changes. So, you can see the effects of all this, the design requirements have come higher. So, if you use these design requirements to verify the existing platform against the allowable stress method, surely none of the platform's design life could be extended. But then the question will come, should we shut down the platform? Yes, if you do not want to do the certification using this ultimate design principle. So, what is the owner's worry? Whether we can operate the platform, whether it is going to collapse or whether it is going to fail during the operation. So, that is the question will be asked. So, to ascertain the safety, we want to make sure that the platform is overstressed, for sure everybody knows, but will not collapse in case if you operate, and that is what the idea behind so called the collapse analysis. But we do not want to have a situation where the ratio between the required collapse capacity and the collapse capacity of the structure should be having a margin, and that is why it is called the reserve strength ratio. This is the absolute reserve strength, because this is not something similar to our working stress factor of safety of 1.6, 1.67. Here if you exceed, it will fail, whereas in allowable stress method we still they will not fail, because you are only working within the elastic limit. So, basically in the operating storm cases, this will be used for most of the time recertification of the platforms. For accidental case, this is just to get a time frame for repair work. If you have a reserve strength ratio, damaged structure versus and undamaged structures, how much time we can permit, basically depending on what will be the storm condition that you are going to allow. For example, I allow only a 1 year storm condition in the evaluation of damage case, then within 1 year I have to repair it, bring back the structure to undamaged condition. So, this reserve strength ratio is an important parameter of a comparison of ultimate strength of full system, either before damage to after damage, and or comparing with the storm conditions, whether 1 year or 100 year. The other thing that I just want to give you an idea is, how do we absorb energy in addition to structural members? There are several ways of doing it. Even in jackets we provide this. For example, we just now designed a protecting member, one horizontal device, just a structure. It absorbs by denting, absorbs by deflection, both elastic and plastic. Now, imagine if we can incorporate a mechanism by which I do not want to damage the member, but somehow I can absorb more and more energy by means of a device which is implanted into the system or implanted into the structure, which will be good. So, that I do not need to replace every time, is not it, because I can make the structure rigid, but by impact the structure is able to take more or absorb more energy. So, you see first thing on the right side, that will be interesting to see. You see a structural connection between a member that is taking directly the impact and the structure which is basically the jacket leg. So, in between we introduce a sleeve pipe in pipe. So, you have outer pipe, I have an inner pipe, both pipes are basically molded together with a rubber element. You see here in the hatch down there. So, when an impact occurs, this rubber will allow the movement of the inner pipe into the sleeve, which is the outer pipe, basically trying to do some work by deflection of the rubber element. Very simple idea, only thing is needs to be designed appropriately, that it will not fail or it will not be too stiff. So, that is where the idea. If it is too stiff, no deflection will happen. If it is very flexible in by impact, it will definitely damage. So, basically for required capacity, these rubber elements can be designed appropriately and molded together and supplied by several specialist vendors, available in large capacities like 1000 tons, 2000 ton capacity. Only thing is, when you have such a element incorporated here, the jacket legs should have sufficient capacity to receive such a loads. So, you need to design for it, and this we call it sock cells, is nothing but a rubber element absorbing energy by means of deflection. So, this is normally used for almost every jacket, because you will provide protection on all 8 directions, diagonal, 4 orthogonal. So, that no damage will happen to the jacket legs, because we know very well if a jacket leg is damaged, what will happen? The jacket is gone, and to protect against that we provide sock cells. And you see on the left side, instead of spending like that, you actually bring in the rubber element in the front. This is basically a conventional way of fendering. You provide a fender rubber element. So, the ship will come in contact with the rubber and the rubber will deflect and the energy absorbed. Only the residual energy will be absorbed by this structural member and the load transfer will happen. Either way, of course, the energy absorption by this rubber will be very, very small compared to this type of the focused shock cells. Depending on the design, you can select any one of them. Mostly we use this type of design for port and harbor structures. You will see if you go to a Chennai port or any port, you will see a lot of rubber fenders hanging around, so that the ships can come and berth against. Whereas in the case of jacket structures, we provide this for protection. But of course, in jackets also we do provide this type of fendering for bringing the boards closer. You will see several rubber fenders hanging around, so that you can bring the boat closer, so that people can get transfer from boat to offshore platform. So, in summary, basically design against impact is a simple exercise. Many times that first 3 stages needs to be done by hand calculation: dent, elastic and plastic deformation. The last one is the global platform deformation, and we have just looked at some devices to take additional energy absorption. So, I think with that we can complete the design against the accidental loads. 2 types of problem we have solved. I think one is on the the design of protector. The other day we were looking at one more problem for ship impact. So, and on the fire and blast wall design, though I have not given you an example, you could expect a simple design of a beam or a plate, basically against increased temperature or a blast pressure. You will be given a load, you can come up with the thickness of the plates, different boundary conditions. So, in here what you have learned is a slightly different design principle in comparison to what you have been doing for members and tubular joints, where a factor of safety is used. Of course, if you compare the members and joints, there itself there is a difference. In members we limit the design to elastic, in joints we do not limit the design to elastic, we go beyond elastic, but before first crack. So, the capacity defined by a factor of safety, whereas in case of accidental loads we have gone beyond elastic, gone up to the ultimate strength and then give a larger factor of safety. Here the allowable stresses can be increased by 70%. So, you will see that all three things you need to remember and select a suitable method for a suitable situation. I think with this we have completed 5 modules.